Good afternoon, everybody. I'm Devin Mier, the Program Director for the Oregon Wheat League. I'm going to help host today, but I'm going to turn it over to Kate and Nicole to get started.
Hi, everyone. My name is Kate Reardon. I'm a microbiologist here at the ARS. So thank you so much for joining us today. This is our third of this year's Pendleton Science Round-up. And Nicole Durfee, our hydrologist here at ARS, is going to be presenting. And then be sure to join us, same place, same time next week for the final seminar of this series. And we hope to have this series again next year. So Nicole, go ahead and take it away. Oh, you're muted.
Okay, there's always something. All right, good afternoon, everybody. Once again, I'm Nicole Durfee. I'm the research hydrologist here with the ARS in Adams, Oregon. So today's talk will be addressing hydrology specific to dryland agriculture in the inland Pacific Northwest. I did gear today's talk more towards a general audience with a diverse knowledge base, so it's likely that some of these concepts are going to be review for some, completely new for others. I did provide QR codes as we go, so if you want to dive deeper into a topic, you can go ahead and click on those and find out more. If I can change slides. There we go. So I divided the talk into four main segments. First, I think it's important to set the stage by discussing the sort of general characteristics that impact hydrology in the region. Then, as remote sensing tools are an important part of the research in the Hydro Lab, I'm going to provide a general overview of some of these concepts and their applications. The next section will address some of the overarching challenges and some of the research objectives associated with hydrology and dryland ag. And then last but not least, moving into some of the research highlights from the Hydro Lab. All right, to start with, as all of you know, we live in a precipitation gradient here in the inland Pacific Northwest. And it's this precipitation gradient that really drives practice. So the image that you see in front of you was created using PRISM data from Oregon State University. This is open access. If you're interested in PRISM data, you can just go to the QR code you see in your screen. The big takeaway point here is you can see that we live in this gradient from arid conditions in the southwest, moving to more semi-arid conditions up towards Walla Walla, where they receive about 20 inches of precipitation, whereas Lexington Echo often receive less than 10 inches of precipitation on an annual basis. So our precipitation patterns here are the result of multiple factors. Of course, we have the Cascades to our west, and we live in the rain shadow of that. We have the Blue Mountains to our southeast, so we get these interesting microclimates that are the result of that. And we also have these maritime fronts that move in, and that's where a lot of our precipitation comes in hand. So once again, the biggest takeaway here is that we have this precipitation gradient, and then most of our precipitation, since we're in a Mediterranean climate, comes during the cold season. Big takeaway point here when it comes to dryland ag is that soil moisture storage matters, and the antecedent conditions, meaning what happens in the year prior to planting, is important for crop growth in the subsequent season. So these two bar plots, we've got average monthly precipitation on your left-hand side and average growing degree day on your right-hand side. These are for three sites for 6 to 7 years. The big takeaway point here is that our precipitation and our growing degree days are asynchronous. Once again, driving home that point that soil water storage really matters. So when we get our precipitation during the year, obviously is very important because the impact of precipitation in May is going to be different than the impact of precipitation in November, really driving home the point that we need to make sure as much water as we can gets into the soil and that we're reducing soil evaporation as much as we can. I do want to point out one interesting facet here. So once again, this data is for the last 6 to 7 years. And as it turns out, May happened to be the month where we got the most precipitation. Historically, this hasn't necessarily been the case. So very quickly, this is for the Adams station. This is the months with the maximum precipitation for each decade over the last 95 years. Just a kind of general overview of how to read this graph. If you look at the column that says 2020 to 2025, you see that 3 November, that means for 3 years, November received the most precipitation. So once again, the driving point here being that our wettest months are November through January, then followed by May. So given the importance of soil moisture, I'd really be remiss if we didn't talk about the soil themselves. So it goes without saying that soils aren't homogeneous across space. They're often not homogeneous across fields. This can vary with topography, past land management, and so on. This image was created using a web soil survey, and you can find that with the QR code. But main takeaway here, most of our soils are classified as mollisols with some iridosols in the drier areas. Mollisols tend to have good water holding capacity. We have that silt loam texture, which is kind of the best of both worlds, where we've got moderate permeability, permeability being an indication of how quickly the water moves through the soil. So we're well drained, but we have good water holding capacity. Downside of this, of course, is that they're susceptible to erosion. So building off the concept of soil texture is our hydrologic group. Hydrologic group is strongly related to soil texture, and it's a gradient between high infiltration and low runoff, or group A, and low infiltration and high runoff. So your high infiltration, low runoff sites are the bright green that you see here. These tend to be your coarser, your sandy soils. Your low infiltration, high runoff, these tend to be your more clayey soils. So as luck would have it, here in the Inland Pacific Northwest, most of our dryland ag falls within group B and a little bit in group C. This is sort of the sweet spot. So we've got moderate infiltration. So water moves through the soil, but it's not completely percolating through the soil quicker than we can use it. And then we have reduced soil erosion. So once again, this is from Web Soil Survey. And if you're interested in the data, the QR code is right there. So lastly, I wanted to discuss typical soil moisture patterns. I think this is pretty intuitive. It's something we have all observed by living here. But the take-home message here is that we can focus in on the important times throughout the season as it pertains to soil moisture storage, whether that's looking at your infiltration patterns during the recharge in the cooler, wetter months, or trying to minimize soil evaporation during your soil drawdown and in your drier months. Next, a key part of conducting research in this region is really making sure that our research is representative of some of these different conditions. So I wanted to highlight some of the places where we're actually collecting weather data. This map highlights those main locations, although we've got 13 locations total. You can see those on your right-hand side. The instrument of these stations varies a little bit. Most have rain gauges and basic weather instruments. A few have soil moisture and matrix potential as well. If you're interested in the weather data, you can go to the QR code that's shown on the screen, or just feel free to reach out. So next, I want to shift the discussion to remote sensing and hydrology. So just like any tool, remote sensing has its relative advantages and its disadvantages. Begin with we have to discuss the spatial and temporal scale. This is a really important consideration and depends on your question at hand. So this can range from satellite-based data, which can provide, in some cases, regional data twice a day, to your drones, your small unpiloted area vehicles, which provide really high spatial resolution, but are obviously limited by weather and so on and so forth. So where remote sensing can really come into play when it comes to research is when you have data scarce areas, and it can help bridge that gap. We can use the on-site data to augment the remote sensing and vice versa, whether it's using it as ground truthing to, in other words, double check our calculations, or really taking a closer look at those spatial temporal patterns across the region. Another important aspect when it comes to remote sensing, and this is particularly the case when it comes to satellite-based remote sensing, is that we can look across the electromagnetic spectrum. So by this, I mean, we're not looking just at those visual bands like the red, green, blue, like what you're seeing with your phone camera. We can also look at near infrared and shortwave infrared, which are both particularly important when it comes to hydrology, as well as microwaves and looking into radar. So remote sensing platforms, this means the means of transportation for the sensor itself. They range from satellite to piloted, to those sensors that are on piloted aircraft, once again, to drones. The sensors vary a lot, but we've really come a long way, and this technology has been around for a while. So it's a fast-moving area of research, but there's just a lot of data out there. And an important aspect of this, particularly when it comes to satellite-based remote sensing, is that a lot of this data is free and open to the public. So I wanted to highlight some of those resources. Google Earth Engine, for instance, is a cloud-based platform. It's a great way to access both a lot of the data sources, but also a great way to do analysis. And of course, you have QGIS, R, and Python. all of which have multiple packages that allow you to take a look at some of this remote sensing data and do analysis. In particular, I want to highlight Earth Explorer and Sentinel Explorer. These two platforms both have a very user-friendly interface. There's no scripting required. And it's a great way to both visualize the data and download some information. So quick note, remote sensing can be either active, like LiDAR, or passive, or some combination of both. Active remote sensing, like LiDAR, involves a system that provides its own source of energy. So LiDAR, it's measuring the amount of time it takes for that beam of light to come back. A passive sensor, and this is more like what's on your phone, your camera, is measuring the amount of reflectance, the reflected light in a certain wavelength. So, and there's also things like SMAP, which is the soil moisture active passive radar, and that uses both active and passive approaches. But for this presentation, I'm going to largely focus in on the passive sensors. So keeping this in mind, it's the reflectance that really tells us the story. So for example, we know that water tends to scatter blue. The takeaway from this being when you look at water, you tend to see blue. It also tends to absorb in the red wavelength and absorb shortwave infrared, and this will become important in a moment. And when it comes to chlorophyll, we know that the chlorophyll and mesophyll in the plants tends to absorb blue and red, and healthier plants tend to reflect more near infrared. So here you can see some of the key wavelengths when it comes to research in hydrology. So normalized difference vegetation index is a concept that I'm sure most of you are familiar with. If not, no discussion of remote sensing is really complete without addressing NDVI. It's a commonly used vegetation index based on some of those principles that we talked about earlier, meaning that healthy vegetation tends to absorb more energy in the red band, and chlorophyll results in higher reflected near infrared. So ranges from -1 to 1, higher values generally indicating either more biomass or healthier vegetation with some limitations. So you can see this illustrated in the images on the screen. So if you look at the NIR image, and this is near infrared, the brighter areas indicate greater near infrared reflectance. Those are the areas that correspond to more vegetation, whereas the red imagery, the brighter areas, indicate more soil. So a similar concept to that is NDMI, and this is based around the concept of SWIR being something that's absorbed by water that we discussed earlier. NDMI, similar in concept to NDVI, where it ranges from -1 to 1, and higher values are associated with higher moisture content. Using these same principles, we have the optical trapezoid model, or OPTRAM. This looks at the relationship between the shortwave infrared and NDVI for estimating shallow soil moisture. This is the example that you see on your screen now. This is created from Sentinel-2 imagery. So important takeaway here, we can see sort of the green and blue areas, and these are areas where we expect higher near surface soil moisture, and red areas tend to be drier. Also microwave, these are longer wavelengths, so they tend to be used at the regional scale. And then thermal infrared. Thermal infrared is a nice wavelength to use, requires a little bit of analysis, like looking at the air temperature and so on. But you find them on satellite-based remote sensing, and you also can use them with drones. It can be a useful indication of soil moisture and canopy transpiration, and this is all related to the principle that evaporation is a cooling process. So what that means is you look at a thermal infrared image, and cooler areas tend to be areas with higher moisture or more transpiring vegetation. So obviously this is just kind of scratching the surface. There are a myriad of other applications, such as estimating evapotranspiration, which is a combination of soil evaporation and plant water use, to looking at land cover, like the example you see here from NAPE imagery. Important part of this is also integrating those remote sensing based images and data with existing models, or looking at soil data, on the ground data in particular. An interesting application of this also is for weed identification, and that's using those spectral signatures in an image classification approach to look at the density and type of weeds that you might see in an area. And layering all of this on top of topography. So we have digital elevation models that can be used, and this can tell us something about how, for instance, soil moisture, transpiration varies with slope or aspect characteristics. So a quick nod to some of the things you can do with drone data. So sometimes the question requires that we have high spatial detail, such as looking at weed presence or assessing differences in crop vigor over field. So unpiloted aircraft systems, UAS, or drones offer one way to do this. UAS have been around for a while. They're a very versatile platform. There's a lot of different types of sensors that are available, offer really high spatial resolution, depending on the flight altitude and the sensor. Sometimes can be down to a millimeter spatial resolution. So these are just two examples. On the left, you'll see an NDVI map. This is from an early season. And the thing I want to point out here is that you can see, based on the brightness of the green, the differences in crop vigor from the right side of the image to the left side of the image. On the right side of the screen, you'll see an example of a 3D model of crop height and density. So this was created using a structure from motion approach, and I'll talk about that in a little bit. But essentially, we've created a digital surface model and draped a red, green, blue image over that. So this gives us an estimate of both crop height as well as density. So now that we've kind of set the stage in terms of regional characteristics and remote sensing technology, I want to take a step back and really discuss some of the challenges associated with hydrology that we hope to address. So I think it's really important to note that hydrology, of course, is just one piece of a much larger puzzle that involves soil chemistry, pathology, agronomy, physiology, and so on. Within this puzzle, I'm largely concerned with the physical properties of the soil and focused on water quantity. So, for example, your physical characteristics of the soil are impacted by tillage, and this impacts aggregates, pore spacing, and so on. I'm also interested in, and this is an important place where we can leverage remote sensing, translating that field scale data to the plot scale and beyond, really making sure that we're providing actionable insight for producers. This involves looking at those spatial and temporal patterns across the precipitation gradient in our area, with the end goal, of course, of making sure that we have resilient systems that no matter what the weather throws at us, we are promoting good soil water management and prolonging agriculture. So at the core of this, once again, is holding onto the water that we get. We can't control the weather, but there's steps we can make to improve soil water retention. So this includes reducing the water that's used by weeds, improving infiltration so that more water actually gets into the soil, maintaining stubble to reduce erosion, encourage infiltration, as well as reducing soil evaporation. So to maximize the soil water we get and we hold on to, we need to really consider the factors that influence soil water capacity. For example, organic matter promotes increased water retention, but also management actions like tillage or cover crops impact bulk density and compaction and your porosity and conductivity. And all of these things impact how well soil moves through the soil. And lastly, we have to consider soil depth. So from a practical sense, there's not much we can do to increase our soil depth, but it's very important, obviously, to make sure that we maintain the soil that we have. And this is where it's really important to make sure we're promoting good infiltration and reducing soil erosion. So I want to focus in on soil evaporation and plant water, collectively known as evapotranspiration. So I think it's important to consider why we study something we can largely not control. We can't control precipitation, we can't control the weather, but perhaps we can do something to reduce soil evaporation. A big part of this research is to simply quantify ET under different conditions across different timeframes. Particularly in the case of soil evaporation, if we understand the factors most influential on ET, then we can start to utilize management to address those factors. So first, of course, it's important to remember that evapotranspiration is controlled by energy, and in this context, that's energy from the sun and water availability, which in this case is your soil moisture. And once again, going back to that second slide, in the inland Pacific Northwest, most of our precipitation is received when we are energy limited. And so there's a number of factors, of course, that influence evapotranspiration. I wanted to highlight a few that are related to management practices. For example, albedo. Albedo is just the reflectance of shortwave solar radiation, surface roughness, and this is going to be impacted by things like residue height, also shading and soil temperature, and of course your vegetation type and the characteristics associated there, but also looking at the microclimate and those factors that influence evapotranspiration, such as wind speed, humidity, and air temperature. And all these things can be impacted by management approaches such as residue. So at the end of the day, we're looking to minimize the soil evaporation, particularly doing fallow, so we can increase water storage. So I did want to cover a little bit about the energy balance because it underlies a lot of the research that we're doing. So evapotranspiration is notoriously challenging to measure, particularly in arid and semi-arid areas. In addition to empirical calculations, so these are things like your Penman-Monteith reference, ET, we often look at evapotranspiration through the lens of the water balance. So water balance being, in our context, incoming precipitation and your change in soil moisture and how that relates to evapotranspiration, or the energy balance, which I've shown here. And this is based on solar radiation and how it's partitioned in the system. So here's a brief primer on the energy balance. We'll start with the net solar radiation. This is just your net shortwave and your long wave solar radiation. This is the energy coming into the system. This is the energy for evaporation or heating the soil or heating the air. It's a factor of soil albedo, as well as the emissivity of your soil and your air, among other factors. Next is your latent heat flux. So your latent heat flux is related to that transition change from liquid water to gaseous water, so evaporation. It's your plant water use and your soil evaporation, and we use this to calculate evapotranspiration. But this incoming energy is also partitioned into sensible heat flux, and that's your air temperature change and your ground heat flux. So particularly in arid climates, your ground heat flux is important. And you can think of this as the energy that's stored in the soil, and similar to conductive heat transfer, which is just the movement of heat along a gradient through mass. Simply put, you can think of it as like if you put an ice cube in your hand, and it's the movement of heat in your hand through the ice cube. This can be particularly important because if we can lessen the ground heat flux, then perhaps we can lessen soil evaporation. So moving on to the goals of the hydrology program, as water is one of the most limiting factors in dryland agriculture, the hydrology program is seeking to improve soil water conservation and wheat water use efficiency at its core. This research will provide key information to producers regarding how the combination of weather patterns, topography, and management impact soil water conservation, and therefore the water that's available for crop use. Key parts of this are looking at the relationship between management practices such as residue management, cover cropping, and tillage. Obviously, quantifying evapotranspiration like we discussed earlier and seeing how this varies across growth stages, how it varies across the precipitation gradient, and how this varies across topography. And then once again, leveraging those remote sensing tools so we can really translate from the plot scale to the field scale to the regional scale and provide these tools for actionable insight, such as considering what are ideal precipitation zones for implementing cover crops. All right, so finally, I'm going to discuss a few of the research projects in the Hydro Lab, starting with the infield evapotranspiration study, and then moving into a couple of the collaborative projects with Oregon State University. These involve topics that are particularly relevant to producers in the region, such as tillage and weed management and cover cropping. So the infield evapotranspiration project is a relatively new project. It began in 2024, starting with 3 sites across the gradient. We've one in Athena, one in Adams, one in Ione. These were all planted in wheat last year. Adams and Athena will be going to be planted in peas this year, with Ione going to fallow. And we're putting in a 4th site here in about a month in Lexington, and that's going to be planted in spring wheat. So taking a closer look at the study design, one of the key points is that we want to look at the methodology that's available for calculating evapotranspiration. Each approach has its relative advantages and disadvantages. So leveraging those advantages, hopefully we can provide a better quantification of water use. First, one of the approaches we'll be looking at is eddy covariance, and this is considered sort of the gold standard when it comes to evapotranspiration, but it's got some limitations, particularly when it comes to spatial variability. So in layman terms, eddy covariance is really looking at the difference in relative humidity over over the movement of a parcel of air to give us an idea of that latent heat flux. Also looking at the energy balance versus the water balance, and then looking at remote sensing options. So these are surface energy balance models from satellite-based resources as well as from the drone. Data collection, once again, we'll be looking at those energy fluxes, looking at the weather data, also looking at soil moisture and matrix potential through the soil profile, and then using NDVI and thermal from drone-based imagery, and then taking canopy height and leaf area index measurements throughout the growing season. Big takeaways, what we're looking to achieve with this project, looking to quantify crop water use and soil evaporation. Once again, leveraging the advantages of each of those methods to come up with a better quantification of soil water use, soil evaporation and plant water use. Also looking at the responsiveness of the system. So what I mean by this is looking at what happens when we get a precipitation event. How quickly do we see soil moisture recharge? How quickly do we see an uptick in evapotranspiration? And where is this occurring in the soil profile? And lastly, we're looking to characterize those factors that are associated with evapotranspiration. So in addition to management approaches, looking at things like the vapor pressure deficit, which is related to relative humidity and evaporative demand, as well as soil moisture levels. The idea here being that we hope to gain a better understanding of what the main drivers are of evapotranspiration in our across our precipitation gradient, so we can leverage this to really impact management approaches. And then once again, looking at remote sensing data like NDVI and NDMI as predictive tools. So this is just some example data, and I'm looking at the time, so I'll push through this a little bit quicker. This is from our Athena site. So Athena is our higher precipitation site. And this is from the growing season from last year. A couple interesting things here. I think you can see the responsiveness in the system. And I should say the soil water content is shallow soil moisture. So we can see an immediate uptick in mid-February associated with that precipitation event. We can see the drawdown in evapotranspiration that happens between aphesis and maturity and how that impacts the soil water. So this is how it plays out across our 3 different sites. Ione being our driest site, Athena being our wettest site. So you can see that both the time frame of peak ET as well as the total quantity of evapotranspiration varies across the precipitation gradient. And this is probably what we'd expect. Moving on to the UAS-based imagery. So the examples here, this is multispectral imagery from our field in Adams. It's high resolution imagery, got red, green, blue, near-infrared, and thermal infrared imagery. On the left-hand side, this is looking at an RGB image to look at crop cover, identifying areas that are a little bit patchy. The center image is our thermal infrared. This is our canopy temperature. Darker areas are cooler areas. So these are areas that we'd expect there to be more soil moisture. And if you look at the image on the right, you can see how some of the darker areas on the thermal infrared image correspond to some of the darker areas on the NDVI image. So as I mentioned earlier, high resolution UAS imagery can also be used to make 3D estimates. This example is from a wheat field in Ione in May of 2025. So brief primer, your digital surface model is an estimate of your canopy height. Your digital terrain model is an estimate of the actual ground surface. You take the difference of the two, and that gives you a canopy height model. What you see here, the brighter areas indicate areas of taller crop. The darker areas are areas of shorter canopy height. So I like this image because it shows you how some of that variation that might not clearly be visible without remote sensing now can be addressed. So this is some of our satellite-based imagery. This is from the harmonized Landsat and Sentinel-2 data. These are 2 separate satellites, but they have similar wavelengths. They capture in similar wavelengths. So this is looking at NDVI and NDMI. Once again, Ione is our lowest precipitation site, and Athena is our highest precipitation site. In general, Athena tended to have higher NDVI and NDMI, and that tended to last longer throughout the year. All right, moving on to our collaborative studies. So the Weed Management and Dryland Wheat Fellow Systems is funded through their Herbicide Research Initiative. This is led by Judith Barusa, the Oregon State University weed scientist, examining tillage and integrated weed management approaches. The overall objective is to look at best management practices and how these can be used to maintain weed control. From the hydrology side, we're largely looking at soil infiltration as tillage is known to impact infiltration. We're taking soil cores at key points throughout the year, and we're also conducting soil moisture surveys. What you see here on your left-hand side is a UAS-based imagery. Here you can see some of the weed cover. The darker areas are areas where there's more weeds. And on the right-hand side, one of our soil moisture surveys. The darker areas, the darker orange areas are areas where there's low moisture. So you can clearly see that there's spatial variations in the soil moisture that are associated with weed presence. So some of the expected outcomes from this project from the hydrology lens, really looking in at water use efficiency and precipitation use efficiency between those treatments, as well as looking at the spatial temporal variability and soil moisture and how that relates to weed presence, and looking at infiltration. And lastly, I wanted to highlight the Resilient Dryland Farming Alliance. This is a project that many of you are familiar with. It's collaboration between OSU and USDA-ARS. Lead PIs are Christina Haggerty on the OSU side and Curtis Adams on the ARS side. It's examining the impact of different cover crops at an intermediate site here in Adams and a low precipitation site in Lexington. It's an interdisciplinary site studying multiple aspects of cover crops, ranging from pathology to soil microbiology to physiology and weed science. From the hydrology side, we'll be taking, or we have been taking soil cores at key points throughout the year, and also looking at shallow soil moisture as an indicator of spatial variations in water use. Additionally, we'll be looking at infiltration and shallow matrix potential, really to get a better idea of how cover crops are impacting the soil water retention curve. So big takeaways here. One of the big ones is to quantify cover crop water use and really getting a better understanding of how cover crops perform in the low and intermediate site and how this translates to how much water is actually available at planting. And then looking at the impact of cover crops and infiltration, whether the presence of roots and that biomass results in increased water infiltration of the soil. And then lastly, looking at the soil water retention curve. So for those of you who may not be familiar with the soil water curve, it's essentially the relationship between soil water content and matrix potential. Matrix potential being an indicator of how much energy is actually needed to extract water from the soil. So the drier the soil, the more difficult it is for plants to overcome that forces that hold water in the pores. Practical application of this is it's an indicator of water retention and therefore soil evaporation and water availability for crops. So here's a few more resources if you're interested in diving into some of the geospatial data. And I'd also like to give a big thank you to the support of our producers and the Oregon Wheat Grower League, as well as our OSU collaborators. And finally, as the hydro program, the Hydrology Lab is largely a field-based program. This really wouldn't be possible without the hard work of our hydrologic technician, David Robertson. So I'll leave it there. If you have any questions, feel free to reach out or feel free to ask now.
Thank you, Nicole. Are there questions? Nicole, can you go back to the QR code slide, please?
Yep. Do you see it?
Not yet.
Okay. It says that it's paused. So I'm going to stop share and reshare.
Okay. We'll also be posting recordings of the videos at a later date. So we'll send that out with the different channels through Devin with the Oregon Wheat Growers League and also through ARS. But if you're wanting one of the videos right now, just reach out to me and I can get a link to you. Okay, now it's good. Thanks, Nicole.
Okay, yeah, no problem. If anybody wants the weather QR code, I can go back to that slide too. Oops.
And Dave has a question.
Sure.
That was fantastic, Nicole. I really appreciate the depth and the explaining things for a microbial ecologist from a hydrologist perspective was really helpful. So thank you. The question I wondered about, and I shared this in a question with Kate in the chat, teams was I would expect that either farmers or regional areas would be really interested in seeing sort of a time lapse. Here's what happened to your farm or your farming community over a growing season, or over two growing season, and maybe for curiosity, but then also maybe say, well, this is what happened, this is what we experienced, and then maybe to see that information and then work with either the extension or with you all about what could I have done, looking back when we really had no rainfall, like you said, that one year, all happening in May, or just I'm a very visual learner, and I'm of course curious about my own environment. Are those kinds of data available, or would that take sort of a specialized team to do that for a community, maybe under contract, or is it something NRCS does, or anybody? Just curious what you know about that.
So my probably very unsatisfactory answer is going to be it depends, and my knowledge is just scratching the surface of what's available. And it depends on what trend you're looking at. So if you're interested in like evapotranspiration as an example, there's platforms like OpenET, which utilizes Landsat data, and there's multiple surface energy balance models that are used. It's very user friendly. I mean, I would suggest anybody using it to kind of dig in a little bit, because all those models have their limitations. But things like that, where you can literally just zoom in on a field, and you can see the estimated evapotranspiration throughout the season. I think it goes back to 2018 now, but I'm not sure about the start date. So there's things like that, depending on the question at hand. There's some other things that would require a little more expertise, and depends on how much time you want to spend learning it and what your question is. But there are a lot of open access resources out there, like PRISM, like the Western Regional Climate Center, like OpenET, like Web Soil Survey. I don't know if that answers your question.
It does, and I thought it wasn't unsatisfactory at all. It made me think of one of our scientists, who's now retired, but I think the effort still exists. Jeff Herrick developed a tool called Land PKS, Potential Knowledge System, designed as an app for a farmer to decide what's the best system to grow on my fields based on soil, climatology. But they were starting to bring in other connected data, so visualization of the NDVI was really impactful, communicated a lot to me just visually. Again, Jeff's retired, but I'm curious who in ARS is still managing that. But what you just presented, if there's opportunities for developing tools, again, that could be, you can click on your iPhone and see here's what's happened on my field the last few years. And yeah, that makes sense from my own historical knowledge of what happened on my fields. But just as another way for farmers, land managers, crop advisors to get a little bit more information. But I'm just thinking out loud, but thanks for a thought stimulating talk. So appreciate it.
Oh, that'd be great. I definitely would like to look into it, because I think it's really important to take some of these concepts, and I want to be able to translate them into something that's actually applicable. So that's a great suggestion. Thank you.
Yeah, thank you. Thanks.
Are there other questions for Nicole? Well, thank you so much, Nicole. I also want to announce that next week we'll have Tom Ducey from South Carolina presenting, and his talk will be taking control of your soil's health, influences of amendments, biologicals, and management. He's our outside guest speaker for this seminar. So we only have 4 spots left for next year. So if you're interested, it's very popular, so be sure you get your name in if you'd like to speak next year. But thank you all for attending today. Hope you enjoy your day. And thank you, Nicole.
Thank you. Have a great day.
Okay, thank you.